topic of this lecture is spectroscopy and the structure of atoms. So why do we need to know about these subjects for forensic science? In forensic science, when you want to identify an object, often you need to know what it's made of. One of the aspects of knowing what it's made of is knowing which of the chemical elements are present in that object or that sample. Spectroscopy and the structure of atoms is the key knowledge for understanding how we can determine which elements are present in a sample, how we can do an elemental analysis on a sample. Well, when and why would we want to do elemental analysis in forensic science? Forensic science is a pragmatic science. It's a pragmatic subject. So the answer to the question of when you would want to do an elemental analysis is whenever it gives you the information you need to proceed with the investigation. So here are three examples. A poisoning. Suppose there's a suspicion that someone has been poisoned with a toxic element such as arsenic or a heavy metal such as lead or chromium. Then you would want to analyze the body fluids for the presence of those elements. We'll talk more about this in the lecture on toxicology. Another example is going to be in our lecture on determining the time of death. Analyzing the chemistry of bones can give you information about how long those skeletal remains have been in the ground. And we will also see that analysis of the elements present in bullets can give us important forensic information about the use of firearms. At the end of this lecture, we'll look at three cases in which the analysis of the elemental composition proved to be very important. One of those cases is the investigation into the body part that was found on the banks of the River Thames. This was back in 2001. Another case is the investigation into the assassination of US President John F. Kennedy, and particularly in trying to answer the question of how many people fired at the president. And the third case is the investigation into the death of the Emperor Napoleon. Now, what is an element? The ancient Greeks considered that matter was made up of 4 elements. That concept was discarded long ago, and our current concept of elements comes from the Anglo-Irish chemist Robert Boyle, who lived back in the 17th century. Boyle's proposal was that elements are substances that can neither be created nor destroyed. And we'll see this concept that elements cannot be destroyed as very important in forensic science. He also said elements are substances that cannot be broken down into simpler materials. So they are the basic building blocks for all the materials that are around us. And Boyle's concept of what is an element has served us until today, though we have to clarify it a little bit. When we say cannot be broken down, it means cannot be broken down by chemical means, because of course elements can be created and destroyed in nuclear reactors by nuclear means. So the Greeks had their 4 elements. How many elements do we consider there are now? There are 93 naturally occurring elements, and then there are additional elements such as plutonium, for instance, that have been created by nuclear technology. Some of those naturally occurring elements are actually very familiar materials. Hydrogen, for instance, the oxygen in the air that we breathe, the carbon that is an essential element making up all living things, and then metals, for instance, like iron and silver and zinc and tin and so on, which we come across in our everyday lives. These are some of the very common naturally occurring elements. And then there are more exotic elements which we don't come across in our normal lives, like uranium. There's one we've heard of. Many more that most people have never heard of, like iridium, samarium, gadolinium, krypton, antimony, and so on. These elements are the basic building blocks for all the materials around us. Let's go back to Boyle's notion that elements cannot be created or destroyed. Let's consider a piece of paper. Paper is made of cellulose. Cellulose consists of the elements carbon, hydrogen, oxygen. So atoms of those elements are assembled in a particular way, and that is cellulose. Suppose I burn a piece of paper, then all the carbon of the cellulose will be converted into carbon dioxide, and all the hydrogen in the cellulose will be converted into water. But the atoms of carbon, which were in the cellulose, are still atoms of carbon, it's just they're now in carbon dioxide. And the atoms of hydrogen that were in the cellulose are still atoms of hydrogen, but they're present in water. If we consider a more complex object, such as a human body, we are made up of many elements: carbon, hydrogen, oxygen, lesser quantities of nitrogen, phosphorus, sulfur, calcium, sodium, potassium, iron, and so on and so on. If you burn a human body, the elements are not destroyed. It's just those elements will be converted into different forms. So the carbon in us will become carbon dioxide, the hydrogen in us will become water, nitrogen will probably end up as nitrogen oxides, phosphorus as phosphorus oxides, and so on. So the elements themselves, their atoms are not destroyed, it's just they become part of other molecules. If there are other elements in your body, for instance, if you have gold or mercury fillings in your teeth, then the gold will probably still remain gold after the body is burned, and the mercury, that will become mercury oxides. But those elements, even though they're not naturally present in the body, they are still not destroyed, and that means they can be detected afterwards. 93 is a lot of elements. The elements were organized back in the 19th century into the famous periodic table, and this was done by the Russian chemist Dmitry Mendeleev. And his periodic table is essential to understanding the chemistry of the elements. There are alternative ways to organize the elements. For instance, the Harvard mathematician and musician Tom Lehrer organized them musically, and his organization may not be so useful to scientists, but it's a lot more amusing. Now, let's talk about what things are made of. And let's consider the case of a bullet. Most bullets are made of lead, but no bullet is absolutely 100% pure lead. So the bulk composition, what most of it is lead. And it may be well over 99% lead, but the bulk composition is not the whole composition. Any object will contain small amounts of trace impurities. So alongside the lead that makes up this bullet, there will be very small amounts of impurities. And in the case of lead, common impurities might be the elements silver and antimony. These trace impurities can be very important because while almost all bullets are made of lead, that is common, the trace impurities will differ from one batch of bullets to another batch of bullets. So studying the trace impurities can help us identify where that bullet came from. So when we're talking about analysis of elements, we're talking about two things: determining what is the bulk composition, but also detecting and analyzing the trace impurities, those elements that are present in very small amounts. and often it's the latter that is the more informative for forensic scientists. So how do we do it? Well, if you think back to high school chemistry, then you would think of something like this: a row of colored test tubes where you dissolve stuff in acid and add reagents and see color changes and precipitates and so forth. And this technology was developed years and years ago, centuries ago, and we don't really use it anymore. The problem with these classical chemical tests is that they require relatively large amounts of material because you have to see with your own eye the result. They are destructive. You have to do chemical transformations on the material, so therefore the evidence is going to be destroyed in the test tube. They are also subject to interference because we are talking about analyzing objects that contain multiple elements. So the analysis for one element might interfere with another element, and you can get interference, and therefore the results can be difficult to interpret and unreliable. On the other hand, they do have some advantages. They are often fast, they're often easy to do, and they require simple equipment such as a test tube. But despite these three advantages, we no longer use them because modern methods have superseded these old chemical tests. Now, when we talk about small quantities, how small is small? Well, let's get an idea of how small can be by looking at the SI prefixes for units. So in the SI system, the metric system, the basic unit of weight is the gram. Well, a gram is not very much. So often, if we are buying stuff in the grocery store, for instance, you might buy a kilogram. So kilo is the prefix which indicates 1,000. So a kilogram is 1,000 grams, and if we want to go bigger, we have a megagram, which is 1,000,000 grams, which we usually refer to as a ton. But we're interested in smaller quantities. So when we go down in size, we come to the milligram. The milligram is 1,000th of a gram. A milligram of material is typically big enough for you to see with the naked eye. If we go down another step, we come to the microgram. A microgram is 1/1,000,000th of a gram. That is an extremely small amount. You cannot see it. But with modern techniques, it's not difficult to be able to analyze for it. Below a microgram is a nanogram. A nanogram is 1/10000000th of a gram. Below that is a picogram being 1/1000000000th of a gram. So a picogram seems to be an extremely small amount of material because it's only 1/10000000th of a gram. But even a picogram is a lot of matter when you compare it to the size of an atom. So 1 picogram of material would contain, say, about 100 billion atoms. So it's a small amount, but it's still a lot bigger than an atom. Now, when we talk about trace elements, we often refer to the amount of the trace element present in a unit called a ppm. And ppm stands for part per million. And 1 ppm is 1 part in 1,000,000. So if you have a ton of material, 1 gram of that material would represent 1 ppm. To give you an idea of the scale of a ppm, if you consider Singapore, the population of Singapore is approximately 5 million people. So detecting 1 ppm of the Singapore population would be equivalent to finding 5 people in Singapore. So a ppm is a very small amount. Finding 5 people in Singapore would be very difficult, but finding 5 ppm of a chemical component of a mixture is something we can do relatively easily with modern technology. Smaller than a ppm is the ppb. ppb stands for parts per billion. So 1 ppb is 1 part in 1 billion. To put this in a similar context, the population of the entire world is about, at the moment, 7 billion people, 7,000 million. So detecting 1 ppb would be finding 7 people in the whole world. Detecting elements at the ppb level is also possible with modern technology.